The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
A couple of announcements. The contest ends today, 5 o'clock. Get the email to my address. Wednesday will be the test 1, and I'll say a few words about that. Coverage through the end of Electron Wednesday. So what I'm talking about today, I will not be testing you, but maybe you might pay attention because about a month from now, we will ask a few skill testing questions about it. But it's one of those pedagogical things. If I test right up until the last thing I say, I don't think that gives you enough dwell time. Now, the flip side is there's going to be a couple of lectures now where it's not going to be on the test, so I think you'll deal with it. Monday I will be giving a seminar on engineering education in Halifax. So in my place will be Professor Ballinger, who will competently substitute for me and keep the ball rolling. But I'll be back Tuesday, and you can contact me if you have some questions in connection with the material. So first thing, I'll begin with comments about the test, and that way if we won't have to worry about running out of time at the end. So the test is Wednesday, the 29th, and it'll be written during the normal class time. So if you take the test at 11, come here, but there's a plurality of rooms because we want to have some vacancies here, all right? So if your last name begins A through K-E, you'll come to this room. If your last name begins K-H through Y-A, you go to 5340. That's the gymnasium on the 3rd floor of Walker. There's a gym up on the 3rd floor, and we'll accommodate a couple of hundred people there. And for those of you at the very end of the alphabet, we have a special room for you, 1-190. So everybody has some elbow room. Please go to the assigned room. And by all means, if you're scheduled to attend class at 11, please take the test at 11. Don't all come crashing into 1 o'clock because we don't have the room or the number of exams. So please go to the assigned room. So here's what the mechanics are. You're going to just go to the room as you normally do. Come on in, sit down. That's all you got to do. Just sit down. Right? What's the purpose of the test, by the way? Why do I give you a test? It's to give you a status report. A status report. I want to give you some feedback, tell you how you're doing. Tell you how you're doing soon. So there's 2 messages I can give you. Either keep up the good work, or you better change your strategy because you're not mastering the material. That's all I'm trying to do. I'm not trying to run a cross-check on the admissions process. As I told you, I believe that everybody that's in this room has the intellectual apparatus to pass this class. So there's no gamesmanship here. If you've been investing the time that I've asked you to, you'll pass handily. There's no tricks, right? You can look at old exams, you can look at your homeworks. That's the kind of questions you can expect. Yeah? Nothing to broadside you. On the other hand, if you haven't been keeping up, I hope that you won't pass so I can tell you, look, you got to do things differently. That's all. Bring 5 things with you. Got 5 fingers, 5 things. Periodic table, table of constants, and you're allowed an age sheet, an 8.5 by 11 sheet of paper. You can write anything you want on it. You can write on the front, you can write on the back, you can write on the edge. I don't care. You can photocopy, you can photo reduce, you can take everything from the last 10 years of 3091 and make it in microdots. I don't care. Whatever you want. So that's 3. Periodic table, table of constants, age sheet, something to calculate with. There will be some computations. So something to calculate with. And I don't care if it's a programmable calculator. The only thing is no wireless devices. And this has wireless internet in here. You're not going to be sending emails during an exam. No computers, no wireless devices. And Lord help you if a cell phone goes off. And last thing, something to write with. And believe it or not, I have students walk in and first thing a hand goes up and says, do you have a pen? Can't believe it. Make sure you got batteries that are in a good state of charge in your calculator. We don't have 450 calculators for you. And you'll write. We'll give you the question paper. You just fill in on the paper, hand it in. You don't have to bring any paper. At 55 minutes, we'll start you at 05. We'll stop you at 55. Stop when we ask you to stop. Out of courtesy to your classmates, everybody might like a little more time. But 55, you stop, and we'll have people collect them either down here or at the back, and we'll get you out of here in an orderly fashion. So that's the mechanics. Now, strategy. I want you to do well. I want you to be able to put your best foot forward. I don't want you to get all frustrated and fail to show what you know. So here's a couple of tips. First thing, read the test. That comes as a big shock. A lot of people don't read the test. They just open it up and they just start working. You know, there's going to be, I don't know, 4 or 5 questions. Well, I just put them down in the order they came out of my head. I don't put them in any strategic order. I don't put them hardest first, easiest first. I don't even think they're in a chronological order by topic. I think it's just whatever. I said, well, I think let's do something on, I don't know, pick a topic. What are we asking them on? I can't remember. We've got them. They're all made up and ready to go. But pick a topic. Pick something about the periodic table. Maybe that's number 1. But maybe that's not your strong suit. So don't start on number 1. But you don't know that there's an easy one for you down at number 4 if you haven't bothered to look at number 4. So take a couple of minutes, read the entire test, and zoom in on the easiest question for you. That way, 2 things happen. First of all, you build some confidence. Secondly, you settle your nerves, and then you move in ascending order. The second thing is, try every question. Try every question, because I give part marks. It's not all about the number. I only give, I don't know, about 10 or 20% for getting the right number in a computation. I tell my graders, if the student demonstrates minimal acceptable proficiency, that student has to get a passing score. If it's out of 9, it's got to be 5 out of 9. If it's out of 10, it's got to be 5 out of 10. If the student hasn't mastered the basic concept, we will make sure that the grade scheme gives a failing grade. So if you demonstrate something by writing an intelligent answer just by saying, outlining it, say, well, what I do is I'd equate the energy and then solve for lambda, I can see that you know what's going on. I can give you 5, 7 out of 10 for that. And then the person actually plugs in all the numbers and gets the right number, we'll get 10. But if you say, well, I don't know how to do this, I'm not going to bother. Don't grade the paper. I'll grade the paper. I have some people say, oh, I'm not doing this well. I forget it. No, keep going. Keep going. And leave tracks. Write your thoughts. You don't have to write everything in equations. You could give me an outline how to solve. Work parametrically to the greatest extent possible. Right, as soon as you see, let's say you got to go through 3 or 4 operations to get a final number. Well, do it algebraically. I have some people, as soon as you see, oh, they got the frequency here. Oh, E equals H nu. I'll plug in. E equals H nu. So I plug in. Let's look up H. They plug in 6.6 times 10 to the minus 34. So I plug it in. They make a keystroke error. Right off the bat, they got some number that looks like for the wavelength, they got the distance from here to Chicago, and they're going to drag that through the whole calculation. What are you doing that for? You know? Conservation of keystrokes. Don't touch the calculator to the last line. Work parametrically, because I can grade easily. I can look at that and go, she knows what's going on. 8 out of 10. Boom, we're done. Got the wrong number, forget it. She's got a good grasp of the material. Instead, right off the bat, you got some stupid number. You're dragging that through the calculations. You got negative wavelengths. You got square root of -1 for something else. Focus. Answer the question. You know, don't play games with me. I start talking something about the Bohr model. You start giving me some core dump about what you know about the Bohr model. It doesn't go by the pound. I've read an entire page full of words and given it 0 because it's not on topic. Just be surgical, give me the answer, and move on. But don't start snowing me. You know? My graders are smart. Smarter than you. They are. I've got smart graders. Do your own work. I mean it. Do your own work. Here we're terrorists. Keep your eyes on your own paper. I don't want to see anybody like this. You see that? I'll just go up. I'll reseat you. And by the way, if you ever feel that you're in a compromising position, someone's pressuring you for information, just raise your hand and ask to be reseated. We don't ask any questions as far as we know. The person next to you has BO. You just want to get out of you just take yourself out of the situation. Just take yourself out of the situation. And by the way, this business of working on every problem is important, because I've seen some people, they start working on number one, but that's not their strong suit. So they spend, let's say you got 4 questions, you got 50 minutes, take out 5 minutes to read the paper, it's 45 minutes. That's roughly 10, 11 minutes per question. There's some questions might be a different length. So you spend 10 minutes on number one, they haven't solved it yet, so another 5 minutes, 5 more minutes, it's 15 minutes, now they're getting steamed. 20 minutes, it's 20 minutes into the exam, they're still working on number one. And then they get really angry, say, I'm going to solve this if it's the last thing I do. Sure enough, 11:55 comes, it's the last thing they're doing. Now think about the math. Let's do the math here. Suppose there's an epiphany at 11:54, and you get a perfect score on that question, and it's worth 25% of the paper. You get 25 out of 25. Terrific, right? You got 0 on the rest because you didn't write anything. Do you see what I'm saying? Try all the questions. So, and good luck. I mean it. There's no attempt to deceive. Come prepared, and you'll do fine. And our goal is to grade those things and get them back to you the following day. We'll give a rapid turnaround. And we'll post the model solutions. And there'll be a different exam in the afternoon, but I think it only makes sense for you not to discuss the paper with people that are taking it in the afternoon. I'm trying to run a school here that has some standards of professional standards. Okay, and there'll be plenty of information to the website and whatnot. All right, well, let's get on with the lesson today. Just to refresh our memories, last day we looked at the average valence electron energy as a measure of reactivity, and en route we discovered that we can divide the periodic table into metals, which is about 75% of the periodic table. These have low average valence electron energies, which means that they're very good, these elements are very good electron donors. And up in the other extreme are elements with very high average valence electron energy. These are electron acceptors. They cling to their electrons quite tenaciously. And subsequently we looked at photoelectron spectroscopy, which is a technique that allows us to determine binding energies, ionization energies being just one example, but we'll see later on that PES can give us other important information that we can't calculate. And then towards the end of the lecture, we started looking at reactivity, and we put up this hypothesis that our observation is that octet stability seems to be an attractive electron configuration. So we saw the noble gases, and then we said, you can also achieve octet stability in electron transfer if you look at elements that are just a little bit rich of electrons versus octet stability, or a little bit lean of electrons. And so we got to ionic bonding, and I think we just got to the point where we were able to start looking at the energetics of that, and we ran out of time. So I want to resume that. I think I managed to get to this point here where I show what happens when the cation here, sodium, is in contact with the anion here, chlorine. And we reasoned that these two eventually reach some kind of an equilibrium separation, which we're using lowercase r to represent. This is the separation measured from the center of the sodium nucleus. And there's this separation, which is a balance of attractive forces, because the chloride is net negative and the sodium is net positive. But both of them, regardless of net charge, have electrons. And so when they become very, very closely spaced, there's mutual repulsion of those electrons. And so there's a repulsive term here. And so the balance of the attractive term and the repulsive term eventually leads us to this situation where we have the equilibrium spacing. And this equilibrium spacing is denoted R sub 0, or R naught. And R naught really is nothing more than the sum of the radius, the ionic radius of sodium, and the ionic radius of chloride. So that we could just say R plus R minus gives you R naught. And right off the bat, you notice that I'm making a huge assumption here. I'm modeling the ions as hard spheres. I'm modeling them as billiard balls of a finite dimension. And so they eventually reach this equilibrium position. And we saw last day we have a Coulombic force of attraction, which we've seen before. Cation is +1, anion is -1, but it doesn't have to be. This could be magnesium. Magnesium would be 2+, so in here you'd put 2E. Or I could have an oxide here, so I would put -2E. In this case, we just have 1 and 1. And then the repulsive term, some positive coefficient, and R to a very high number. N lies between 6 and 12, and this is known as the Born exponent. The Born exponent. This is a very high number because it depends upon electron-electron repulsion. These electrons, first of all, there's many of them, and they're in motion. They're moving at very, very high speed, and so the result is that this repulsive term is very, very intense, but very short order. So beyond a modest distance, you don't feel the electron-electron repulsion. So you need the mathematics to imitate reality, and that's why this is such a high number. And down here, what do we have? We have the sum of these two bottoming out. See, at very, very high values of R, 1 over R dominates. At very, very low values of R, 1 over R to the 10th dominates. And in between, the two cancel, and here we are at the minimum, and we can find R naught by looking for the minimum. So how do we get the minimum? We differentiate dE by dR. We take d by dr equals 0 at R equals R naught. And coincidentally, what's the partial of energy with respect to distance? That's force. So what am I saying? The net force is 0. Attractive and repulsive forces are balanced. So everything makes sense here. And we can solve this, and if we do so, we can actually get a handle on that Born exponent by solving the equation. And I'm not going to do it. I'm just going to put it up here without taking time. And so what I get is the energy of the system at the equilibrium separation is given by minus Z plus. This is the most general form. This is the valence, the charge on the cation, times, I'll common factor this. So the charge on the cation times E, the charge on the anion times minus E, so there's the minus E squared, and divided by 4 pi epsilon 0 R naught, because this is now I'm evaluating this function at R naught, 1 minus 1 over n, where n is the Born exponent. And this applies only at, obviously, only at R equals R naught, but that's good because that's the equilibrium separation. So that tells us the energy of what? What have I formed here? I formed a bond, an ionic bond. So this is the energy of a single ionic bond. The energy of an ionic bond. And what do we notice? We notice that E, the value of E at R naught, is negative, as it should be. It's a negative number. And what are the characteristics of this bond? Well, there's two things that I want to highlight. First of all, it's omnidirectional. Omnidirectional. What do I mean by that? There's no preferred direction. Could form in any direction because the field, the Coulombic field, is radial in all directions. There's no preferred orientation. Okay? The field is radial. This is the electric field. So there's no preferred direction. And the second thing is it's unsaturated. Unsaturated. What do I mean by that? Well, I show you one sodium and one chloride. There's nothing saying that that sodium, its positive charge hasn't been neutralized. It still has positive charge, and there's nothing saying another chloride couldn't stick to it. Or yet another chloride, and another sodium sticking to the chloride. So this means it's not a strict bond one-to-one. It's not monogamous, is another way of putting it. Okay? So it allows for plurality of bonds from any ion. From any ion. Plurality of bonds can form from any ion. And if you take all of these ideas, omnidirectional and unsaturated, it means that ions can keep glomming on, and that result is we get large arrays of ions. Well, what does that give us? Well, if I have a large number of species glommed together, that means it's going to be solid at room temperature. because gases exist as discrete particles. So we have either single atoms, molecules consisting of small numbers of atoms. You don't have gas molecules consisting of thousands of atoms. When you get thousands of atoms, things start to condense because there's a capacity to form other bonds secondarily, which we'll get to in a little bit. So just take it on faith. If you have a large number of atoms in an aggregate, it's going to require that the substance turns solid and condense at room temperature. And the word array is loaded. These don't just sit down anywhere. They sit down in a special way. And so what you're going to end up with is, well, let's go over that. Here's sodium and chloride. They keep attaching and attaching and attaching, but we've got two sizes. We're modeling them as hard spheres, and so they're going to fit together in a regular array. And so this means that they will form a crystal. So we're going to have solids and we're going to have crystal. What do we mean by crystal? Crystal is an ordered solid. An ordered solid, as opposed to a disordered solid. And we'll talk about both in a little bit. All right, so now I want to show you that this comes necessarily from an energetic standpoint. It's a really cool derivation. I want to compare two situations. Here's an ion gas. This is my humble drawing to indicate discrete sodium-chlorine pairs. So this is one of these pairs that I've shown up here. It's got a negative energy. We see that we get a negative energy by attaching the chloride to the sodium. And I'm saying suppose these form as they have to initially in the gas phase, and they remain two atoms per ion pair, discretely bombing around in the gas phase. So that's situation number one. Situation number two is I take the same number and I make a row. They're all in one row. So what happens if this is, I've only drawn three, but now let's pump up the volume here. Let's get in Avogadro. So if I have Avogadro number of these things in a long line, you can bet it's going to be a solid. It's going to be a one-dimensional crystal. So the question is, can I show you from an energetic standpoint that the crystal is favored over having the discrete set of pairs? And you know the answer is yes, because I wouldn't set myself up for failure like this, would I? So let's take a look. First of all, situation number one, well, you know how to do that because you know the energy of one pair. So let's just multiply that by Avogadro's number. So E1 will simply equal N Avogadro times the energy of the ion pair at R equals R naught, which we can then substitute N Avogadro. I'm doing this for a 1-1, plus 1 minus 1, like sodium chloride. We can make it more complex later. And you have to get N from experimental evidence. You can't pull that out of theory. So this is the Born exponent is determined experimentally, and there are tables of that. All right, so now let's get the energy for the line. So for that, I'm going to draw a line of these. So I'm going to start with, I'm going to get the color chalk because the doctor says it's good for me. So, all right, so here's the sodium and the chloride on each side, and then we'll go for another sodium and then another chloride on each side. And so now what I want to do is I'm going to start here at the center, and I'm going to count the energetics, right? And what I'm going to do is I'm going to say start with this ion, add up the energy associated with the interactions between that ion and everybody else in the row, and then multiply it by Avogadro's number, because that's the number of atoms there are in a row. So sauce for the goose is sauce for the gander. You say, yeah, what about edge effects? I got Avogadro's number of these things. What do you think the error is going to be by failing to recognize that at the end of 6 times 10 to the 23rd, I've overcounted some energy? It's vanishingly small. So don't get preoccupied by the end. Work the big middle, and the middle is everything here. So we can start. This distance here is R naught. So I know the energy in this first pair. The energy in the first pair would equal. That's just going to equal minus E squared over 4 pi epsilon 0 R naught. That's just what we've seen before. But in addition, there's the field is continuing to radiate. So it's unsaturated and it's omnidirectional. So this cation feels the repulsive force of the cation over here. This cation is attracting the chloride next to it, and it's repelling the sodium as the next nearest neighbor. So that's a repulsive term. I've got to add that up. I've got to put that in because that's a repulsive energy, and that's going to decrease the energy of the system. So I've got a distance here of 2r naught, and at a distance of 2r naught, I have a positive repulsive term. I just plug into the Coulomb's law, and so that's going to be plus E squared over 4 pi epsilon 0 2r naught. Now what happens? Let's keep counting. Now the next one is a chloride. It's of opposite charge, and it exerts an influence. Only that's minus to plus, so that's going to give me a minus term here. That's 4 pi epsilon 0 3r naught, and so on and so on. I think you can see the way this is going. So what about the Born term? Forget the Born term. The Born term isn't going to be felt except in this first one. So I'm going to forget it now, and then I'll patch it in at the end. All right? You don't need Born repulsion at 2r naught. That's a waste of memory. All right, and then what are we going to do? Oh, we got to do this. I'm only counting in one direction, so I got to multiply this whole thing by 2 because I got to count in both directions. And so now I'm going to common factor this, and I'll get minus E squared over 4 pi epsilon 0 r naught times 2 times this series, 1 minus a half plus a third minus a quarter, etc. Okay? So what we've got is this series is broken into two terms that are conveniently representing two physical ideas. This is electrostatics right here. The prefactor embodies all the electrostatics. And what's all this stuff? Why is it 1, a half, a third? This is the instant geometry. Or the atom, that is to say, the instant atom arrangements. The instant atom arrangement. In this case, it's a line. So, now what I'm going to do, this is off of just that one central cation. So now let's do it for all of the ions. So what I'm going to do now is I'm going to multiply by n Avogadro and then add Born repulsion. Add Born repulsion. And we put all that together, and here's what it looks like. It looks like this. Equal to minus n Avogadro E squared over 4 pi epsilon 0 r naught 1 minus 1 over n. And I'm going to call this whole geometric factor here, this whole geometric factor, I'm going to put it into one number, and I'm going to denote that the Madelung constant. The Madelung constant. The Madelung constant is simply the geometric factor. That's a number. All right? So let's put that here. And so now the question is, what I'm trying to prove to you is that E2 is more negative than E1. So ultimately what I want is, what's the relative magnitude of E2 over E1? What is it? Is it greater than 1? That's the question, right? If I can prove that it's greater than 1, that means that the line is stabler than the set of ion pairs. And if you look at this series, you know this series log of 1, what's the series expansion? Log of 1 plus x is, what is it? It's x minus x squared over 2 plus x cubed over 3, etc., etc. If you plug in x equals 1, that's our series. 1 minus a half plus a third, it's all there. So if you go and work that out, log of 2, and you got 2 log 2, by math you can show that for the line, our series, m, is equal to 2 natural logarithm of 2, which is 1.386, which is greater than 1. So what have I shown? I've shown that by taking Avogadro's number of individual ion pairs and putting them all together in a line, the system's energy became more negative. So that's to say that it's favored. So we could say an energy level diagram, this would be energy, here's 0. If this is the energy of the pair, let's make this E over E of the ion pair. E over E for the pair. So this is 1, all right? And we've just shown that for the line, so this is pairs, Avogadro's number of pairs. This is Avogadro's number of ion pairs in a line. That's 1.386. And then if you go to the real sodium chloride crystal and you do this same calculation but in 3 dimensions, so that you take every sodium and you count all of its nearest neighbors, next nearest neighbors, next nearest neighbors, not only on a line, but in the plane and above and below in all 3 dimensions, and go through that calculation, it's even more negative. It's 1.7475. Conclusion, if I start to react sodium with chlorine, the result is a crystal, a 3-dimensional array, because at every point, first thing happens, electron transfer. Why? To get a stable octet. The result, I've got ion pairs. Pluses attract to minuses. Minuses attract to pluses. They start glomming together, but they don't stop with 1 plus 1. 1 plus 1, and then the ion pair grabs another one, and before you know it, you have a crystal. So this is simply the energetics of crystal formation. So this is a 3-dimensional crystal. You can consider this line a 1-dimensional crystal because it's ordered. It's ordered, so I call it 1-dimensional crystal. So this says that when it comes to ion pairs, when it comes to ions, that line dancing trumps ballroom dancing. That's what it's saying. See, they'd rather be in a line than dance 2 by 2. That doesn't apply to all things, but it does in this case. Okay, so now let's look at properties. Let's talk about properties. See, we've gone a long way. We started with this hypothesis of octet stability. I'm talking about properties of ionic crystals. They're solid at room temperature. Why? What's the bonds? These are huge energies. These are huge energies. Coulombic forces. All right? High melting points and boiling points. Why do they have a high melting point and boiling point? Because when you ask yourself that question, you should consider what is the thermal energy versus the bonding energy. If the bonding energy is very strongly negative, thermal energy isn't great enough to disrupt those bonds and allow those bonds to be broken and then have fluidity. So strong bonds means high melting points and boiling points. Transparent divisible light. Transparent divisible light. Crystals are, the sodium chloride crystal is transparent divisible light. I know table salt is white, but that's because you've got powder and you've got multiple surfaces scattering. But a large crystal of sodium chloride is clear and colorless. And it's faceted. You can see that it has the shape. If you take one of those individual grains of sodium chloride, look at it carefully, you'll see the edges look like this. Why is it transparent to visible light? Here's how you ask that question. When you want to know if something's transparent to visible light or not, here's the mystery material, and here's visible light. And what is going to allow for absorption or some interaction with visible light? Inside here, you've got electronic states. And you've got to ask yourself, is the energy difference here, the delta E, in the electronic states, how does that compare with the E of visible light? What's the E of visible light? You know, it's about 2 to 3 electron volts. About 2 to 3 electron volts. This has what? Sodium plus. It's isoelectronic with neon. Chloride minus. Isoelectronic with argon. What do we know about the average valence electron energies? We just saw it the first slide. It's up around 13, 14, 15 electron volts. This thing is going to touch it. It won't lay a glove on it. So what happens? It goes through? Nothing. Nothing. All that glitters is not gold, but it must have free electrons. This has no free electrons. They're all bound. So that's how you determine if something's transparent. It's going to be electrical insulator. There's no electrons to move around. They're all bound. Hard and brittle. Why? Because we've got strong bonds. Strong bonds means the material will resist an applied force. You apply a force, the material will resist it until you have a force great enough to break the bonds. So you don't have ductility, which is what you have in metal. That's what makes metal so fascinating, because metallic bonding allows the atoms to glide over one another without resulting in catastrophic failure. Whereas ceramics, ionic crystals, will resist until they shatter. There's only 2 categories. It's either elastic with full resistance or destruction. Again, the bonds. Soluble in water, other polar solvents, we'll have to come back to that later. They melt to form ionic liquids. Ionic solids form ionic liquids. So that's I showed you last day what happens when they form, and we were able to electrolyze and make fantastic metals like magnesium. Okay, where do we find these ionic crystals? Where do we look? Well, you need electron transfer, so you need a donor and you need an acceptor. So where are the good donors? Donors are over here, the metals, on the left end of the periodic table. And where are the acceptors? On the right side of the periodic table. So if you take some from column 1 or 2 and you mix it with some from column 8 and 9, bingo, you've got reaction. So here's an example that shows, here's some very, very metallic elements, groups 1 and 2, and some non-metallic elements over here, 5, 6, and 7. And so you can imagine that if you mix these, if you take sodium and you mix it with chlorine, you get sodium chloride. But there's nothing saying you can't take magnesium and mix it with oxygen and make magnesium oxide. And you would expect that that would be a much stabler compound, because instead of +1 attracting +1, now you have +2 attracting attracting -2, +2 attracting -2, so the Coulombic forces are much, much greater. And that'll be reflected in what? Higher melting point, higher boiling point, greater resistance to reactivity. So does it strike you odd that maybe magnesium oxide, one of its applications would be refractories, that is to say brickwork in high temperature furnaces, maybe tiles on the shuttle to resist high temperatures because of the high internal bonding? You see, there's a system here. Chemistry isn't a litany of facts. We started with a few simple assumptions. And look at what we're doing now. We're designing systems. We're building engineering systems, making materials choices. It's fantastic. Okay, so we can do this one more time. Let's do one more time. I want to show you something else. I want to show you another way to get a sense of these energies. And for that, I want to look at the energy starting from real material. See, up until now, I've been talking about gas phase, single atoms, all this stuff. So let's look at this reaction. Sodium solid plus chlorine gas. It's a diatomic molecule, and I want that to react to give me sodium chloride as a solid and crystalline. I want it ordered solid. So for this, I need to invoke a couple of bits of science. First one is Hess's law. Hess's law states that for any chemical reaction, the energy change is path independent. Path independent. That is to say, I can now reroute that sodium plus chlorine reaction and go a different way, but I still end up with the same change in energy. And why? It's because it's a state function. It's the same thing as gravitational energy. Whether you take the elevator to the top of the Hancock Tower or whether you walk up the stairs, the change in gravitational potential is identical. You might be winded doing it the second way, but when you get to the top and you're at the 60th story, your gravitational potential is independent of how you got there. And that's what this is saying. It's an analogy. Energy change is path independent. So now I'm going to break this into elementary steps and look at the relative contributions. So what did we do so far? We talked about this reaction here where we had chloride ion in the gas phase plus sodium ion in the gas phase, right? We started with gaseous sodium to make gaseous sodium ion and gaseous atomic chlorine to make gaseous chloride ion through electron transfer, all in the gas phase. Very idealistic, but it's not the way the world works. So I want to get to there starting from real sodium and real chlorine. So first thing I'm going to do is I'm going to convert the sodium into vapor. So this is sodium goes to sodium gas. And then I'm going to take sodium gas and I'm going to make this into sodium gas plus electron. Oh, by the way, this is called sublimation, isn't it? This process, sublimation, solid to vapor, sublimation. This is called ionization, isn't it? Gas phase species loses an electron. That's the strict definition of ionization. So I'm already there with sodium. Now chlorine, I got to do a little bit more heavy lifting here because chlorine starts as a diatomic molecule. So the first thing I got to do is bust that in half. And so this is called dissociation. So I need to dissociate the chlorine rather. And now I've got to convert atomic chlorine into ionic chlorine. So I'm going to do that by adding an electron. And this reaction here is the inverse of ionization, isn't it? Its ionization would be I take one of the electrons on chlorine and throw it away. Here I'm actually throwing an electron onto chlorine. So this reaction is called electron affinity. Electron affinity. So you can think of electron affinity as sort of the ionization in reverse of the ion. It's the minus loses an ion. And this one here, this reaction is what we call crystallization. Crystallization. So those are the 5 steps. So let's see if we can find information. I'm going to call this 1. Let's see, I think I labeled this one 2. Ionization I labeled 3. Electron affinity I labeled 4. And crystallization I labeled 5. And thanks to Professor Hess, I can now say that the total energy to form sodium chloride should equal, in other words, delta H to form, delta H formation of sodium chloride should be independent of path. So I should be able to take the sum of all of those delta H's. Oh, I'm using H, forgive me. This is the term enthalpy. Enthalpy, it's essentially equal to internal energy for condensed systems, but when you look in the books, sometimes they'll use this term. So as for a first pass, let's just say for condensed systems we can go with it. So we're going to take the sum of the delta H's, or the deltas H, for all of these little reactions. Okay? So let's go. Let's get some numbers here. We got some numbers. Let's see. Oh, no. This is called the Born-Haber Cycle, what I'm showing you right now. And this was put up by 2 people, Max Born and Fritz Haber. And actually, I put this up. If you're interested in reading about these people, you can go. There's a Nobel Prize website. You can learn about all these guys. So this is Haber. He got the Nobel in 1918. He invented ammonia synthesis with catalysis by iron. Brilliant chemist. Born worked on a number of things, including the Born exponent, and taught himself crystallography sort of as something to do during World War I. And that's how come he got involved in this, because obviously this is talking about crystal formation. So that's why this is called the Born-Haber Cycle. So anyways, if you go to your periodic table, you'll find that on the one side you can get what's called the enthalpy of atomization, and that's this first term. Delta H1 is enthalpy of atomization. And if you look it up for sodium, it's about 108 kilojoules per mole. Actually, what I did, I used a different source. So I have 107, but it's okay. What's a kilojoule between friends? All right, number two is dissociation energy, and dissociation energy is 122 kilojoules per mole. And number three is ionization. So if you flip the periodic table over, you'll have the ionization energy of sodium, first ionization energy, and it's about 5 eV, which when you convert is a whopping 496 kilojoules per mole. This is looking bleak, people. Look at this. I've got 3 out of the 5 energies, and they're all positive. This thing's better start turning negative soon, or we're going to change the way the world works here. And I know that sodium chloride forms, because if I look on the web page of 3091, you see this down here? This is sodium in kerosene. That's metallic sodium that we're keeping kerosene so it doesn't react with the oxygen in the air. And that's an Erlenmeyer flask that's been filled with chlorine, and sodium has been added to it. And there's the sodium chloride crystal that forms between the two of them. So I know, because I looked at the website, I know this reaction's got a negative number. There's an interesting observation about electronic structure, by the way. Sodium, metallic sodium, is toxic to humans. Chlorine gas, toxic to humans. Electron transfer, we cannot live. We die without sodium chloride. Okay, so this tells you that it's electronic structure that governs. All right, so let's find some good news here. Well, I got some good news. Number 4, electron affinity. Chlorine's got a high valence electron energy. It gobbles up electrons, and that's a negative number. That turns out to be negative 349. That's for part 4. And then the last one, huge. If you go through the Madeline calculation, it's basically this one over here, multiplied by 1.7475, and you end up with 787, minus 787 kilojoules per mole. So when you add this whole thing up, it gives you a net of minus 411 kilojoules per mole, or about 4 eV per ion pair. So, good. Whew, I was worried there. All right. So that's the Born-Haber cycle, and the Born-Haber cycle allows you to see what the relative values of the different energy components are. Born-Haber cycle. And again, what's the utility of the Born-Haber cycle? It deconvolves that reaction of sodium plus chlorine into elementary steps that are related to electron transfer and acquisition. So that's the value of Born-Haber. Here's a chart that just shows there's the positive energies, and you can see the various components, then the negative energies in a net. But look at the lattice energy. The Madelung energy component is huge, which tells you that when the ions form, they really want to continue to glom onto one another and form that giant crystal. And so this is now a chart of just component number 5, the lattice energies. Keep this number in mind, 787. All right, let's check. Here's sodium plus chlorine is 787. So that's 1 plus against 1 minus. But look at this one. There's magnesium with oxygen. That's 3791. It's almost 4,000 kilojoules per mole. And magnesium oxide has a melting point of 2,800 degrees C. Sodium chloride is about 801 degrees C. All right? Aluminum oxide. Look at aluminum plus oxygen. Look at this. Aluminum oxide, almost 16,000 kilojoules per mole. Alumina is really stable, which is why it takes so much energy to make aluminum. That's why aluminum is so expensive, because the oxide is so stable. And why is it so stable? Because aluminum ions have charge of +3, and oxygen ions have charge of -2. So when you go into the Coulombic term here, instead of 1 times 1, it's 3 times 2. That's it. So you want bricks? You want high temperature bricks? What are you going to make them out of? It's pretty obvious. It's all here. All falls out. It's fantastic. It's fantastic. And this is an interesting thing. This is ionic radii with a noble gas configuration. So all of these have engaged in electron transfer. So just to get your bearings, there's our pal sodium. Sodium plus. So sodium plus is isoelectronic with neon. It's only got 10 electrons, not 11. But magnesium 2 plus, it's also isoelectronic with neon. What do you see? You started with O double minus, so that's oxygen plus 2 electrons. It's 1.45. 10 electrons again, 1.33. 10 electrons again, 10 electrons again, 10 electrons again. What's happening? Same number of electrons, but the number of protons keeps going up, 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 up. The positive force of attraction of the electrons on the outside is greater and greater, and that pulls everything in. And so not only is aluminum highly charged, but it's small. It's physically small. So it's, tight, buff, lean, mean fighting machine. It goes after oxygen. See? Because it's small. It's high charge density. And likewise down here. So you see all of these. Look at beryllium. Beryllium 2 plus. Very, very tiny. Charge +2. Now, why do we need to know all this? I mean, I can take you, immediately we can start designing batteries, because we need ions. We need ions in motion. We need ions, small ions in motion. All of this stuff is related. Fantastic stuff. So what you see is that the radius changes with atomic number for constant electron number. Yeah. Well, we're getting close. I talked a lot about the exam, so I don't have a lot time left to talk about the structural metals. I'll just give you this one little slide so you get a sense of what we're up against. Here's number 1 structural metal is steel. Number 2 is iron. Aluminum. Number 3 is magnesium. Aluminum and magnesium are both made by ionic liquid electrolysis, just as I showed you last day. But look at the tonnage differences. Here's aluminum is 25 million tons per year for the whole planet. Magnesium was 600,000 tons. Iron, steel, 800 million tons. Almost 1 billion tons of steel. That's virgin metal. That's not recycled. And steel is the most recycled material. It sells for about 20 cents a pound. So that represents about a third of $1 trillion. 20 cents a pound. You build a steel plant with a capital cost of several $billion. You bring iron, ore from one part of the planet, carbon, limestone. You put it into this reactor, and you ship this all over the world. Go to the grocery store tonight. Tell me what you find on the shelf that sells for 20 cents a pound. This is amazing. This is modern industrial chemistry showing its strength. All right, before you go, I'll send you, it's a weekend, so I'll send you off with a joke. So we studied the uncertainty principle, Heisenberg's uncertainty principle. So the story goes, Heisenberg is given a seminar. He's got a rental car. He's zooming back to the airport. He's doing 100 miles an hour down to Mass Pike. He gets pulled over by the state trooper. State trooper said, I want title registration. He says, hey, buddy, where's the fire? You know how fast you were going? And Heisenberg says, no, but I know where I am. Get out of here.